Anyway. Hello and welcome back to Calculus 1, right? The Saturday edition. We have section 3.8 on implicit differentiation. This is where we put our chain rule to use. So implicit differentiation is something that something different than the entire chapter, actually, because this is what you use when you have an expression that is not a function. You see, if I consider, why is this blue? If I consider a circle and I pick a point on a circle, that point has a tangent line to it, right? And we know that the slope of that tangent line is the derivative computed at value a. So if you work the logic backwards, there has to be a way to take the derivative of an expression that is not a function. So that's how this 3.8 gets to be the oddball in pretty much the entire Calculus 1 curriculum. All right? Every single section other than this one is applied to a function. This is the only one that is applied to, well, both function and non-function. So what is the equation of the circle? It's x squared plus y squared equals to, let's say, 9, right? If the radius is 3. Let's say the radius is 3. So I have equation, and it's clearly not a function because it has y squared. You can also see it's not a function because it fails vertical line test, right? Not a function. So now, there are no formulas to learn. This is a procedure that you are learning. And it's utilizing the chain rule idea. The notation is a little bit different. You say d dx, and now you put the entire expression inside these brackets. So we never had equal within the brackets before. This is the first and only time you will have equal in the brackets. So the question is, what is the derivative of a circle where circle is not a function? And the answer is simply, well, the derivative of x squared is 2x. So it's the same thing. And the derivative of y squared is, well, it better be 2y. But here is the trick. You are taking the derivative of y in respect to x. You have to follow this with a chain dy dx. And that's the focus of this lecture, which is what I have to explain. And then equals to derivative of 9 is 0. So where is the new stuff? The new stuff is technically just this piece. Now, as you can see, you can solve for it, right? You can say 2y dy dx is equal to negative 2x, and then dy dx is equal to negative 2x over 2y. 2's cancel, and you have dy dx equals to negative x over y. This is the derivative of the circle, and of course it's going to look weird because it was not a function. It has a y in it, in the answer. You never had a y in your answer when you did previous. Y was not even mentioned anywhere since the beginning of chapter 3. All of a sudden, y is the part of it because, again, this is different. The implicit differentiation takes derivatives of non-functions. So, can I have more of these? The answer is obviously yes. Say we have the derivative of 3x to the 5 plus y to the 6 minus cosine y equal to 4. You can plug this in Mathematica and see what it looks like. It's going to be some kind of line, right? Definitely not going to be a function because y to the 6 because of cosine y and so on. Not going to be a function. You will have to have some squiggles for vertical line to fail, right? Now, what do? I take the derivative of this term by term, and every time, listen to this very carefully, and any time when I have variable mismatch, I have to follow by a chain. Anytime I have a variable mismatch, I have to follow by a chain. I can follow by a chain all the time. Now, this is the time when I'm really going to ask you to put your pens down, one of the rare times, and stare at the screen because I need you to hear what I'm saying as I am writing it. This is what's going on in the head, right, as I'm taking this derivative. It will make a big difference for you. The derivative of 3x to the 5 is 15x to the 4. I took the derivative of x in respect to x. Plus, the derivative of y to the 6 is 6y to the 5. I took the derivative of y in respect to x. Minus, the derivative of cosine is negative sine y. I took the derivative of y in respect to x. The derivative of constant is 0. I don't need, this cancels to 1. You see that? So it doesn't matter what variable I have. I'm just going to plow through the derivative the way we learned in the beginning of the chapter. The derivative of x squared is 2x. The derivative of y squared is 2y. No new stuff there. What's new is if the variables don't match, you must follow with the chain. Now, you see that the derivative, that the variables on the first one did match. Yeah, they cancel to 1. Technically, if I was to teach this first, and then the entire chapter 3, on the first day, when I taught nx to the n minus 1, I could have said y is equal to x squared. Take the derivative of that. The derivative of y is 1, right? And then I took the derivative of y in respect to x equals the derivative of x squared is 2x. I took the derivative of x in respect to x. What's the next line? The next line is dy dx equals 2x, right? This is exactly the derivative. See, this thing overarches everything we did. When you take the derivative of x in respect to x, you will get dx over dx, and we never wrote it. Never, right? Was it there? Yes, it was there all the time. It was there with the chain rule, and it was there with the trig integrals, and the time before that, and the time before that. Since day 1, when you've seen the derivatives, that dx was always there. And we never wrote it because dx over dx is just 1, and 1 times 2x is 2x. So why bother? Going back to our previous problem. 5 times 3 is 15. X to the 5 minus 1 is 4. I took the derivative of x in respect to x. Dx over dx cancel. You know that there is no chain for this piece. You know that there is no chain. Hop to the next one. y to the 6. It's the same as x to the 6, right? 6 y to the 5. I took the derivative of y in respect to x. They don't cancel. Leave it there. Leave it. Same for cosine term, derivative of constant is 0. Now you are at this line, and now you have to go and fish out dy dx. Dx is gone, right? That's 1 times this is just that, right? So now, factor this, keep this to the other side, factor dy dx, and have it dy dx equals everything else. These problems are going to be ugly all the time. All the time. They have to, right? You're not dealing with a function. When you see the ugly problems dealing with a function, now you don't even have a function. Obviously, every problem is going to be ugly, right?
So what would y in terms of y be?
1, and then dy dy.
Okay, so
but then dx would be dx over dy, and that stays. Oh, we'll do that. It's coming up. We are going to disconnect ourselves from x and a y in that sense. And we're going to completely make a new thing. We'll see. So now what do I have? I have this 6y to the 5 dy dx plus sine y dy dx is equal to negative 15x to the 4. Dy dx, and I'm factoring now. I have 6y to the 5 plus sine y is equal to negative 15x to the 4th. And the final stage is to divide to get dy dx alone as negative 15x to the 4 divided by 6y to the 5 plus sine y. And that's the answer. That's the derivative. Ugly? Sure. But possible. We can take derivatives of equations that are not functions, because we can always find a tangent line. I don't care how twisted the function is. Whee! Right? I can go and I can find a tangent line, and another tangent line, and another tangent line, and another tangent line. There are tangent lines everywhere. The derivative exists along these smooth turning curves. We do not have the derivative on a spike, on a cusp like this. There is no derivative there, there's no derivative there, so no. But it doesn't matter if it is a function or whatever. Yeah, you will have the derivative. All right. So now, your question is going to set us up for a story, for a discovery, right? What is the derivative in respect to m? Now, you are going to see this m as different things. Some of you are going to say money, some of you are going to say mass, some of you are going to say mammals. I don't know if you're in bio, whatever. You are taking the derivative in respect to m. No more x's and y's. And now you have 3m squared minus 6k to the 5th plus sine of m equals to 9m. How about that? This is what you have. We are ignoring the fact that we don't have x and a y. The reason why mathematics uses x and a y is want to make general, right? Here is the set of rules that work in the universe, and now you go find application. Someone screams, population, great, use p in time. So TP become your variables. Someone else screams, physics, mass, great, use mass and time, right? And so on. So what is this? It's just a bunch of letters that are variables put on a pile. So what do I have? The derivative of 3m squared is 6m. I took the derivative of m in respect to m. Minus 30k to the 4. I took the derivative of k in respect to m. Plus the derivative of sine is cosine m. I took the derivative of m in respect to m. Is equal to the derivative of 9m is 9, and I took the derivative of m in respect to m. And then you go and you say, anytime when I have dm over dm, they cancel. Kill, kill, kill. There we go. What do I have? 6m minus 30k square, to the 4th plus cosine m equals 9. Oh, I forgot the dk dm over here, sorry. Move 30k to the other side, move 9. 6m plus cosine m minus 9 is 30k to the 4 dk dm. So dk dm is equal to 6m plus cosine m minus 9 divided by 30k to the 4. Done. Please use words to make this a joke, right? You are taking the derivative term by term, term-wise. So, the derivative of 3x squared would be 6x. So the derivative of 3m squared is 6m. So we're not learning any new derivative rules. We just said, what's the chain on that? The variable m matches the variable we are taking the derivative in respect to. So dm over dm. What is the dm dm? It's this d times this m over this dm. It's this d times this k over dm. Bueno? So, I took the derivative of m in respect to m. I took the derivative of k in respect to m. I took the derivative of m in respect to m. And every dm, dm cancels. Every dy, dy cancels. Every dr, dr cancels. But anytime you have different variables, they stay. They stay. And when they stay, solve for them in the end. How many of these can you have? Which gives rise, you can have any number of them, because we have multivariable functions. Body mass index function is usually what most of the people will know. It takes in account what? Body mass index, it takes in account age, height, and weight. That's the three variables, plus body mass index equals 2. It's 4 variables altogether, right? We all have different age, different mass, different height, so our BMI will be different, person by person, right? So if I'm looking at the derivative of that mess, yeah, it will be all of these. I should have that as an example. So now you understand that we can take technically derivative of anything. Anything. And we will use this in our 3.11 next class to calculate the related rates See, related rates. This is a rate, something divided by something. It's a rate. So when you divide something by something, you get a rate, and said related rates, you have 2 of them or 3 of them or 4 of them, and you relate them. So we'll deal with that. We are already set to understand related rates, because I can ask you to take the time derivative of volume formula for a cube. Cube, right? You know what the cube is. Like ice cube, right? All sides are the same. Cube. Like a dice, right? To play. We will have to understand in 3.11, which is only 3 sections away, 2 sections away, that I can take the time derivative of that, because I want to see how fast the volume is changing if the side is changing. Why would side change? Due to heat. If it's as it freezes, or as you are melting the ice cube, it's getting smaller. If the ice cube is getting smaller because sides are getting smaller, the volume of the thing is getting smaller. We are relating on how fast these things are changing. There's going to be a whole lecture on that, obviously, next time. I don't want to spoil it. But mechanics of that lecture, right, is you taking implicit derivatives. You say derivative of v in respect to t. Well, derivative of v is 1. I took the derivative of v in respect to t is equal to derivative of a cubed is 3a squared dA dt. I took derivative of a in respect to t. We don't have to write this 1, so we just get rid of it. And this is what we are going to actually use to compute problems. So we are able now to say the volume, the change of volume in time is related to the change of side in time, the length of a side in time, which makes sense. The shorter the sides of the cube, the smaller the volume of the cube. The bigger the length of the side of the cube, the bigger the volume. So all of that will make sense when we do the section on it, to take what we learn now into the applied setting, which is the one that makes you money, obviously. Now, the weird one. The weird one is the derivative in respect to y. Right? Because we are always used to talking about derivative in respect to x. But we also have derivative in respect to y. In Calculus 3, it's called partial derivative. I just taught it this week in my Calc 3 class. So we can take derivative in respect to y. It's okay. We can take derivative in respect to anything. Remember, we only care if the variables match or variables do not match. To follow with the chain or to kind of skip it because it cancels to 1. So if I have this, and I have my equation, let's say x squared plus 3 sine y is equal to, y squared minus 1. You can literally put whatever you want. It doesn't matter, right? You can make these problems up and just solve them. It doesn't matter what you put. You just go and do this derivative term by term. The derivative of x squared is 2x. I took the derivative of x in respect to y. You see, now it doesn't cancel on the x derivative. You have to leave it. Plus, the derivative of 3 sine y is 3 cosine y, and it's going to be I took the derivative of y in respect to y, so now they cancel. Equals to 2y, again dy dy, and that's gone. Obviously, to speed the process up, you don't have to write this dy dy or dx dx dm dm. You can just completely ignore those and just keep going with the stuff that you actually have to keep. So now this is 2x dx dy is equal to 2y minus 3 cosine y, and finally dx dy is equal to 2y minus 3 cosine y divided by 2x. You can take the derivative of anything. Anything. It's a pretty cool section. So if you please remember that your independent variable goes in the denominator of the derivative instruction, right? This is the part which says take the derivative of what's in the bracket. Right? That's the meaning of it. So the instruction says this is your denominator. One more example and we're done with this lecture. There's nothing else, right? You only need to learn the skill of variables match or variables don't match. That's technically it. Just move along to the next section. What else do we have? We have the derivative in respect to t for okay. Let's do one more of x. We'll do 2 more examples. Let's do this one first. ddx of 4x squared plus xy is equal to y cubed. What's fun about this one? Can anyone tell me what's fun about this problem? Why is that? Why is that something that might be fun? Can't split them up. They're there. They're multiplied. Why are they fun?
It's tough to find the d of x and the y of x in terms of both of those variables in that one.
So how do we deal with that? How do we deal with that?
I guess you would put dx, and then dy, dx next to the product.
Yes! Product rule. There we go. Yeah, by the way, we can do the chain quotient and product, right? Embedded in all of this mess. Usually this is what I say, good luck. Hey, it's the reason why 2%, right? Are you 2% or you're not 2%? Of course you're 2%. So let's go. You become 1% when you calc 2, but right now, you know, you're 2% now. Next class is 1%. So the derivative of 4x squared is very good. dx. I don't have to write it, but it's dx, right? Plus, and here is my product rule now. Copy the first, derivative of the second, plus copy the second, derivative of the first. And finally, on the other side, 3y squared dy dx. Copy the first, that's x. Derivative of the second, that's y. We're taking the derivative of y. Well, that's 1. But I have to follow with the dy dx chain because I took the derivative of y with respect to x. Usually this is one that kills your grade on the test. So please make sure, right, you make a note of this term there. So now everything with dx dy goes on the left. Everything without dx dy goes on the right, or whatever. So I'm going to actually have 8x plus y stay. On the other side, I have 3y squared minus x as I factor dy dx, right? Because this term goes there as a negative x dy dx. So, and then I factor it. So the derivative dy dx is equal to 8x plus y divided by 3y squared minus x. And that's the answer. The last example is going to be the one that will open the door to further horrors, obviously. Can we find a second implicit derivative and a third and a fourth? And the answer is yes. And that goes under the mathematical gymnastics again, right? Every time I mention mathematical gymnastics means terrible calculations for not that much of the applied payout in terms of engineering and so on. So I would like to take a look at one of these problems, like let's say something cheap. So I'm not planning on sleeping here tonight. X plus, so I want to find, so find second derivative, which it will work out to be d squared y over d x squared, right? And the problem is given as x plus y equals to cosine y. So no product rules, no, you know, excessive calculations. All right. I have my expression over here. And when I do the first derivative of it, I'll have the first derivative. And then I have to do one more time, and we're done. So derivative of x is 1 times dx over dx, plus derivative of y is 1 times dy dx, equals derivative of cosine is negative sine y dy dx. So it doesn't matter if your x's or y's are on the left or right side of the equal sign, the same rule applies to all across the board. You have the variable match, that's cross it out, you don't even have to write it. If the variables are not matched, immediately leave it there. So now this works out to be 1 plus dy dx is equal to negative sine dy dx. Well, we want dy dx, right? So you move dy dx to the, let's say, right. 1 equals to, oops, I forgot the y over here. So sine y dy dx. There we go. So now if you factor the dy dx, you will have negative sine y minus 1. So what's dy dx? Dy dx is equal to 1 over negative sine y minus 1. And I can just factor out minus sign in the denominator and push it up. So dy dx is equal to negative 1 over sine y plus 1. This is your first derivative, right? That's not a question. Question is second one. Now, to find the second derivative, and this is where we start, you have to take another derivative of what you have. And you can quickly see how, you can immediately see how quickly this can spiral into absolute nightmare, right, to calculate. Well, the derivative of dy and dx, that would just be immediately d squared dy, which is what we're looking for. But on the other side, you can choose to do quotient rule or you can do chain rule, whatever. I would prefer a chain rule here, as I have -1 sine y plus 1 to the -1. I would prefer to do that rather than the quotient rule. So the derivative of this would be, well, -1 times 1 is 1. Sine of y plus 1 to the -2. Times the derivative of the inside. The derivative of sine is cosine y, and then I have dy dx following that. So now the problem says that we have cosine y dy dx divided by sine y plus 1 everything squared. Now you can see denominator squared, so you can see that the quotient rule, you know, you will be able to use the quotient rule and you will get the same thing. The evil part about this problem is that we're not done, right? You have that dy dx, you have to go back and plug what that is, because you have it in this black box. So now, d squared y dx squared is equal to cosine y, and then we have -1 sine y, so -1 over sine y plus 1 divided by sine y plus 1 squared. When you deal with the double fraction, you get negative cosine y divided by sine y plus 1 cubed. Because this one is over 1. Cosine goes there, so 1 times negative cosine is negative cosine, and 2 that are close 5, so the same, so cubed. To shovel through that algebra. So you see now that this can spiral out, right, and go become crazy very quickly. But again, practice makes perfect. One thing that I get asked frequently is, how come there were no dy dx's in here? We took the derivative. Well, please note that I never took the derivative of guts. I took the derivative of something to the -1. Something to the -1 is that something to the -2. So I never took the derivative of the inside, which is why there are no dx, dy, blah, blah, blah inside. But once I took the derivative of the inside, there it is. Because I took the derivative of a function of y. It was dy dx right there. So it takes a little bit of time to get used to these things. Again, you've never done anything like this before, so obviously it's new. And but one part is, if it looks intimidating, give it time, give it practice. You are no longer in algebra, but you can sit down, right? You guys are STEM, right? So your brain works that way. You are no longer in algebra, but you can sit and figure out the rule in 2 seconds and be able to do every single problem. Those days are over, right? You have to put in hours into these things to slowly unwrap. And please don't go to the problem 63 right away, right? Two ways that I would recommend to learn this is, note that I haven't solved a single problem from examples that are done in the book. Those examples are wonderful instructional examples, and you should go to them and figure them out and work your way through them. Also, YouTube. YouTube has 100,000 videos on these things. Pick a problem, and generally each video starts with a problem written without any solution. Start the video. Once you see the problem, pause the video. Either completely do the problem or keep working until you stop. Play the video. Follow your work along. You catch an error, or you clear your roadblock, pause the video, fix, keep going, either finish or get stuck. Play the video, right? You have insane power within YouTube to learn this. The only thing it needs is your time and determination and your discipline. I promise you, you're not going to get it in 15 minutes. You can't. It's way too complicated to be done in 15 minutes. It takes time, it takes practice, so you are sacrificing your time to learn this. 311 is going to be this, not the second derivative, but I gave you the cheapest problem right there. This will be done in the first three, within the first three examples in 311 next time we meet. Do not procrastinate either, because clearly, if you don't understand implicit differentiation because you didn't understand the chain rule, what chance do you have in the word problem? And the word problem is going to say the flow here and the flow here, and you know how they're equal, or you're dumping sand on a pile, and where is the radius of the cone it's creating, and height. The two airplanes are coming in at 90 degrees. One needs to land first, right? What is how fast is the distance between them decreasing? All of those questions, they're all in chapter 11. It's 100% word problems. If you don't have the skill and the base for those, it's going to be a living nightmare, right? So please take time. It's going to take a long time to get through these things, but once you learn it, then you know the build-up material later is going to go easier. And always, you know, stop by and ask questions, and we work through problems together. And you know, but the YouTube thing with pause play game can get you to really understand this. So one more time, you find the YouTube video, you just type in chain rule and or implicit differentiation, whatever, you're going to get 100,000 videos. You're going to get Khan Academy as well, right? You see the problem, pause, do as far as you can, or the whole thing, and then play. The first time something is wrong, you fix that, pause, continue, do more, more, and more, and then when you're done with that example, read that example one more time, move to the next video. Do it again, and again, and again. That's called hand-holding, right? As you are, but it's necessary, right? They held my hand until I learned how to walk, right? And I held my kids' hands till they, right? There's nothing wrong with hand-holding, right? We all need it at different stages. So right now, whatever it takes, but please, chain rule is the most frequent derivative you will take. You must know that one. You have to figure it out one way or another. We had a 2-hour lecture on it, or whatever. It was very, very long. That gives rise to implicit differentiation, which gives rise to related rates, which gives rise to your job and your money. So, do it, right? So that's that for implicit. and we'll have the next lecture, which is coming up in a few minutes.